All right, as we said, the performance of your binary search tree, all these different operations, okay, the performance depends on the height of the tree. So if we want the binary search tree to be really useful, to help it to be efficient, we want to keep the height as low as possible, okay? But at the same time, we also know that the best possible height asymptotically is log n. That's basically complete the binary search tree. So we cannot expect the height to be better than that, okay? So that means that we want to keep the height as low as possible. Ideally, we want to make sure that the binary search tree, the height is logarithmic of the size of the tree, log n, okay? So trees of this log n height is called a balanced binary search tree, okay? All right. So intuitively, what I'm showing here is not a complete tree, but it's a good tree because the height is it's low. Most of nodes have both children. Okay, this is a bad tree. Okay, because this here everybody has only one child, which means that the height of this is n. Okay, in this case, so this is a bad tree. Okay, so if I perform binary search operation on this tree, that's too bad because everything takes a linear time in worst case. Okay, all right. As I said that it turned out that there are ways for us to add XOR conditions to the binary search tree, okay, to make sure that the height is always log n asymptotically. Okay, there are different ways to do this. Okay, some popular ones. One of them is called the red-black tree. Okay, the other is so-called Avl tree. So all of this are different ways to add condition to binary search tree to guarantee the height is, as long as those conditions are satisfied, then the height of the tree is log n. Okay, they are more like the relaxation of the complete binary search tree. Okay, why can't we just say that, oh, I want the tree always to be complete? Because that to maintain the complete binary search tree property can be expensive to update. Okay, so all of this balance the binary search tree like a red-black tree or Avl tree. The trick is that to have a condition which is easy to maintain, while at the same time still guarantee that height is still logarithmic asymptotically. Okay, and we're not going to describe such trees, introduce such trees in detail. I just want you to know what all of you to be aware that such trees exist, and pretty much all the standard programming package, they contain implementation of such balanced binary search trees. Okay, so you can, in your own programming, you can use any of those implementation. Okay, one thing I want to point out is that once such a tree is created, okay, you have to clearly, it can then support all these operations, search, minimum, maximum, in time, which is proportional to the height of the tree, which is also big O of log n, because now the height is log n, using all the algorithm we described before. So algorithm doesn't change. It's just that now the tree is nicer, so the time become more efficient. Okay. There are extra work which comes that at handling the dynamic operations, because when you have insertion or deletion, okay, then you have to add a new node or remove a new node from your tree. Okay, if you don't do anything, if you only guarantee that it's a binary search tree, then the height can very soon become not logarithmic anymore. Okay, so I'll give you an example in a minute. Okay, and to handle that, we have to do so-called rebalancing operation. Okay, so what do I mean by that? Well, so imagine that suppose I give you a tree at this point. I have a very nice balanced binary search tree. In fact, in this case, let's say that it's actually complete. Okay, so this is a very nice tree. And let's say right now the height, I have n element inside, and right now the height is log n. Okay, now imagine I'm going to do the following. Okay, imagine that I'm going to insert x1, so k1, insert key2, and I insert n new elements. Okay, so I insert n new elements. So I have n insertion. Okay, and let's say we're really unlucky. Okay, all the numbers that I'm inserting is bigger and bigger, and all of them are bigger than whatever the elements we had before. Okay, what does it mean? So if K1 is bigger than all the elements here, that means when I insert it, I have to go all the way right. And the K1 will be inserted here, right? Because I mean, it's bigger than anything. So when I insert, I have to always go right, okay? And when K2 comes, again, I have to go all the way right, and the K2 will be inserted here, and so on. So after I insert n of them, Kn of them, what do we have? Now, in the new tree, the total elements is m equal to, originally I had n elements, but then I also add another new elements, n new elements. So the total elements now is m, which is 2n. So that's the size of your tree, okay? But what is the height? Well, height is original height, and this new height is unfortunately n. So the height is log n plus n, which is very bad. It's not logarithmic anymore. Okay? So in other words, but this is still valid binary search tree. Okay? So the point I'm making here is that you can start with a very nice balanced binary search tree. But if you have dynamic operation, okay, let's say insertion, and then you can ruin that height. It may not be balanced anymore. Okay? That's why that's the tricky part in maintaining all this balanced binary search tree, is that we have to make sure that when we have dynamic operation, I have to do rebalance to make sure that the total height is still logarithmic. Okay, and it turned out that there are rules for us to do that, and there's a simple, in fact, not too complicated procedure to make sure that the rebalance can work. Okay, so we'll not get into detail. I just want to make sure you're aware of this is the tricky part when you have a balanced binary search tree. You have to do rebalancing. Okay, and the rebalancing itself, and after rebalancing, you make sure the tree is still logarithmic of the size, okay? The rebalance is usually based on the so-called rotation operation, okay? So I just explained the idea behind the rotation. Let's say this is a current tree, okay? I could do the so-called rotation to get a new tree, which is still binary, satisfy binary search property, but the height can be different, okay? Let's say that right now this tree, A, has high height. So A is very long, so the height of A is large, okay? By doing this right rotation, okay, right rotation would basically rotate at X this way. It move Y here and move X down, and we have to put the subtree B and C in the correct position. But it's easy to verify this new after rotation, this still satisfy binary search tree property, still BST. Okay, but the good thing is that you see now this bad branch A, which used to be very long, now become one height shorter. Okay, so we kind of shrink the height. Okay, so this rotation operation is what we can use to change height of the tree, and that's how we use to rebalance after you have dynamic operation into a balanced binary search tree to make sure the height remains logarithmic of the size. Okay, all right, so okay. We're not talking about how the balanced binary search is implemented. This is just a point I want to make. But the key message to remember is that in the binary, if you have n input keys already stored in the balanced binary search tree, okay, then the height is log n. Remember that all this operation take time order of height, which means that it's order of log n now. Okay, so it's no longer linear time. All of this operation, including the dynamic ones, can now be implemented in only order of log n time in the worst case for balanced binary search tree. Okay, if you use a balanced binary search tree. Okay, all right. Now, if you compare earlier when we talk about the using array implementation, remember if you use array, you can do search in log n and the maxima in order 1. So it looks like that, using an array, it looks like that actually here it's more efficient. Indeed, using an array, it's more efficient to answer these queries. However, remember using an array, we would have to spend linear time for all these operations. Okay, which is very, very slow. Okay, because log n can be significantly smaller than n. Okay, so in practice, if you have a database to maintain, then very often you have to have dynamic updates to your database, right? New students come, we need to insert their records. Older students graduate, we have to delete their records, so that you always need this dynamic updates. Okay, so we can use binary search tree in this case to help us to do all of them efficiently. Okay, but then to achieve this, we need to use a balanced binary search tree. All right. Okay. All right. So this is what I want to say about the balanced binary search tree. And next, oops.